Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back to Optimization in Civil Engineering. In the last class, we discussed about the single variable optimization problems. We also came to know about the necessary and the sufficiency conditions of the single variable optimization problem. We also discussed that the single variable optimization problem is not always sufficient for describing or solving various engineering problems. In many engineering problems, you will find that we have more than one design variables. In those cases, if we want to use the optimization technique, we have to use the multivariable optimization formulation and its solution processes. For example, if you are designing a beam and you want to find out what would be the optimum size of the beam, particularly a rectangular beam represented by its height and width. These two design variables are somewhat related and depends on each other. We cannot neglect one variable and optimize for the other unless one is constrained or one is predefined. So in such design, we definitely need to consider more than one design variable for the optimization process. Now, as I was indicating, in certain cases, the values of the design variable could be predefined or could be limited. If it is limited, then we called it as a constraint, and the optimization formulation is known as constraint optimization formulation. So, a multivariable optimization formulation with constraints are known as multivariable optimization problem with constraints. If there are no constraint, then the problem is known as multivariable optimization problem without constraint or unconstrained multivariable optimization problem. In today's class, we'll learn about the unconstrained multivariable optimization problems. We learned about the necessary and the sufficiency conditions for the single variable optimization problems. The same is going to be applied to the multivariable optimization problems. However, the multivariable aspects need to be incorporated in the derivation of the conditions. Now let us see how we are going to incorporate the multiple variable aspects in the necessary and the sufficiency conditions of an unconstrained multivariable optimization problem.
Today we are going to discuss about multivariable optimization. From the previous lecture, you know that if the number of variables in an optimization problem is more than one, then we call it as a multivariable optimization. Now, optimization problem can have constraint or it may not. If an optimization problem has a constraint, then we call it as a constraint optimization problem. And if an optimization problem does not have any constraint, then we call it as an unconstrained optimization problem. So today our discussion is going to be on multivariable optimization problem without any constraint, so unconstrained multivariable optimization problem. Whatever you have learned in the single variable optimization problem is going to be applicable for the multivariable optimization. However, the process is going to be little bit different because the number of variables here are more than one. So let's look into the multivariable optimization problem without any constraint. As I had indicated that an objective function can have more than one design or decision variable, and if we have that, then we call it as a multivariable optimization problem. And the understanding of the single variable optimization problems which we discussed in our previous lecture is going to be helpful here. A multivariable optimization problem can be represented as a function of fx where the x is actually a vector representing multiple variables. Now, in a multivariable optimization problem, there could be constraints, and this constraint, as we had indicated earlier, some of these constraints could be of equality nature or inequality nature. If the constraints are of inequality nature, which is represented here as Gj x lesser equal to 0, then it is going to be represented as shown here. Now here the x again represents a vector which we had indicated earlier, and the inequality constraint could be more than one, so we are saying it could be 1 to capital J. Similar to the inequality constraint, we can have equality constraint which can be represented as hkx equal to 0, where k could be 1 to capital K. Here we have only shown the inequality constraint which is less or equal to 0. There could be inequality constraint where it is greater or equal to 0. We are not going to get much in details of those, as we'll be discussing this equality inequality constraint in a later lecture. Today we'll be just focusing on the unconstrained, which is represented as f capital X. So let's look into the derivatives. A multivariable optimization problem has more than one variable. So if we try to find out the first order derivative, we can find out the partial derivative based on each one of the variable, and the partial derivative can be represented as shown here. Now we also know from our single variable optimization problem, we may need to look into the higher order of derivatives. At this point we'll look into the second order derivative of the multi-objective function. The second order derivative is going to be represented as this way, which if we want to derive, it is going to give us a matrix in this format. So this format, you should carefully look into how it is coming up. We are doing the partial derivative of the multivariable objective function based on first variable and then based on the other variables. So if we are taking the first variable and if we do the partial derivative twice, we are going to get this term. If we do the first order derivative, which we have obtained here, and we try to do the second order derivative based on the second variable, then we'll get this term, and henceforth if we do it for the last variable or the final variable, we can get it this. Like that way we can get all the second order derivative, and it is going to be a matrix, and this matrix is known as Hessian matrix. Now you can see that if we do the second order derivative, we already got a matrix which is essentially a square matrix. You can imagine if you want to do the third order derivative, it is no longer going to be a matrix of n cross n, rather it is going to be a tensor of n cross n cross n. And as we increase the order of derivative, our dimension of this matrix is going to increase accordingly. So it is going to be quite cumbersome if you have to, or if you require to do the higher order of derivatives beyond the second order. Now let's look into the optimality conditions. In the single variable optimization, we said there are two conditions. One is the necessary condition and the second one is the sufficient condition. The necessary condition indicates the gradient, and the gradient is the first order derivative. So if we quickly go back to the previous slide where we have shown the first order derivative, you will notice that the partial derivative of the multivariable objective function with respect to each of the variable represented here is actually indicating the slope of the function with respect to each variable. And if we look into the necessary condition, we can say that if we equate our first order derivative to 0, we can get the points where the slope for a particular variable is going to be 0, and the point where we have the slope 0 can be represented as the optimum point as shown here. It is a vector represented by x star. Similar to the single variable optimization problem, the higher order derivative of the multivariable objective function can be checked for the sufficient condition. So the necessary condition gave us the point where the slope is going to be 0, and the sufficient condition is going to indicate us whether that particular point is good to obtain a minimum value or maximum value, or it is not going to yield any of them, rather it is going to give us a saddle point. So first let us understand when we can get the minimum value, particularly if it is the second order derivative, and if you are checking whether the Hessian matrix which I had shown you earlier is positive definite at a particular point, then the function is going to be minimum at that point. Of course, provided at that point we had the slope 0 or it satisfies the necessary condition. Similarly, at a particular point where the necessary condition had been satisfied is going to yield a maximum value if the Hessian matrix for that point is going to be a negative definite. In case if we find that the Hessian matrix at that particular point is neither positive nor negative definite, then we know that we have reached to a point of inflection. In this case, we call it a saddle point. There could be another situation. This is the case when we say the Hessian matrix is semi-definite. This condition is equivalent to the condition when our derivative was equal to 0. It was neither negative nor positive but equal to 0 for the single variable optimization, and we said at that point we need to further investigate, which means we have to do the higher order of derivative to come to a conclusion. In case of multivariable optimization, if the Hessian matrix is semi-definite, we say that we have to go for the higher order derivatives to decide. Now, as you have seen, the second order derivative had already yielded a n by n matrix, and as I had indicated earlier, a higher order of the derivative, at least let's take the third order derivative, is going to be n cross n cross n tensor. If it is a fourth order, we would get n cross n cross n cross n tensor. So as we increase the order, it is going to be of that many dimensions. So the order decides the dimension. Hence, if we come to a point that the second order derivative is yielding semi-definite Hessian matrix, then we have to go to the higher order derivative, and which could be quite involving to solve the problem. Now we said that the second order derivative has to be positive definite
for minimum function value,
or negative definite in order to function to be maximum. Let us see how we can say a particular matrix is going to be a positive definite or negative definite. There are two ways we can do it. The first way is looking into the eigenvalues. In this case, if we can find out the eigenvalues of a particular matrix are positive, then we can say that the matrix is positive definite. If the eigenvalues are negative, then the matrix is a negative definite. If our matrix looks like this, we need to find out the eigenvalues that satisfy this condition, and in this, if we find that lambda is positive, then we can conclude that matrix is a positive definite matrix. In this case, if we find that if lambda is negative, we can conclude that the matrix is negative definite. So this is one way you can find out the eigenvalues and then you can conclude. We'll look into the second method. The second method is based on the principal determinants. In this case, we have to find out the principal determinants of a particular matrix. So if we have a matrix which is A and which is of n cross n, we need to find out the principal determinants. So the principal determinants are going to be, one of them is this, the second one is going to be this, like that way it will go, and the final one is going to be like this. So we are going to get n number of principal determinants. And these determinants are explained as first determinant, the second determinant, which is this part, is explained here. Like that way, if we go to the nth principal determinant, we get the complete matrix.